Okay, during the last class, you were learning no, you were learning how to look for information. For information given the position versus time graph. You know that the time always is gonna be a graph on the x-axis, which is the axis for the independent variable, and the position is gonna be a graph on the y-axis. Okay, another clarification, and you have to keep that in mind because today we're gonna incorporate some formulas into the calculation of the speed of velocity. Keep in mind that even though the position is graph on the y-axis, we are going to use x to represent position and delta x just to express the difference in position of an object. Okay, so are you ready for today's class? Look at the title. We're going to be calculating speed and velocity algebraically, meaning that we're going to use the equation, and graphically, meaning that we're going to use a graph. Speed and velocity. Do you know what is the difference between speed and velocity? You were learning that when you were in, I don't know, in elementary school? Maybe not. Okay, the difference between speed and velocity. The speed is a scalar. Do you remember what is a scalar? You were learning that. You were learning about that last class. Scalar has only a magnitude. What happened with velocity? Velocity is a vector. What is the difference between a scalar and a vector? That a vector has a magnitude, first name is a number, and also a direction, which is the last name. Yes, you are going to Disney World or you're driving there from Miami all the way through Orlando at 65 miles per hour. That's your speed. But you are going at 65 miles per hour north. That's your velocity. See, for the velocity, you need a first name, which is the magnitude, plus the last name, which is the direction. Okay. The other day we were talking about position versus time graph, okay, and we were talking about a constant rate of change. See, no, because all the graph that we were analyzing, the motion or the position of the objects that we were analyzing, they were represented with a line. You know that when you have a line, it's because the rate of change is a constant. Okay, and we didn't talk about speed and we didn't talk about velocity. We just talk about all the information that you can get from there. Okay, but today, today you're gonna find a speed and velocity. You already know what is the difference. In front of you, you have a graph. Okay, remember that we're using the rectangular coordinating system just to graph the motion of an object, y, and when the y and the x-axis meet, that's the origin. And remember that we're talking about position versus time graph. Okay, position versus time. Oh my goodness, let me share my handwriting. Time is always the independent variable. Position is the dependent. Still in this chapter is going to be represented with an x. Okay, so if we're going to concentrate on objects that are moving at a constant rate. You're going to put it over here. See, you were learning in algebra 1 that is, you want to find the slope of the line is the rise over the run. Okay, if I apply these definitions here to my position versus time line, I'm gonna have a difference in position, see that, over a time interval. And we were discussing that notation the other day. You know that the triangle is not a triangle, it's a Greek letter. Delta, that means difference. So this equation over here is giving me the slope of this line over here, if that line is representing the motion of an object. So let's say that the difference is 6 meters. Okay, so it was moving from the origin all the way through here, 6 meters in, I don't know, 2 seconds. Okay, in 2 seconds. See that? I'm calculating the slope of my line, but at the same time, I'm using unit of measurements. So when you simplify that, you have 3 meters per second. Okay, the slope of the line is 3, and it's positive, meaning that the object is going, but like is moving away from the origin. Okay, and according to the graph, you can analyze that. You can see that in there. Now, meters per second. What is represented in meter per second? Okay, meters per second. You're right. Speed, Ms. Ramos. A speed is represented in meters per second because you are dividing the distance that the object was covering by the time interval that that object took to get to the place. Ms. Ramos, what are you talking about all of that? Because the slope of the line representing the motion of an object is what? Is the speed. See that? Is the speed. And why the speed, Ms. Ramo? Why not the velocity? What is missing here? The direction. So let's say that this is the north and this is the east. The velocity of that object is 3 meters per second. 3 meters per second. I don't know. Let's say that the positive part of is, because it's moving all day, like, I don't know, it's moving to the east coast. But I have to let you know in the problem. If I want the velocity, I want to let you know where that car is moving. Okay, don't get confused. I know that made that mistake. Okay, but it's not notice. No. Over there, I have to let you know which way this car is moving so you can give me the speed plus the direction in order to give me the velocity. Okay, so I'm going to summarize this. And I know that I have a garabato in here. So if I have a time, a graph of position in meters versus time in seconds, the slope of my line is gonna give me what? The speed. That slope with the duration will give me the velocity. The velocity. Now, that speed velocity that I'm getting from the slope is called the average speed or the average velocity. Okay? Remember that the difference between the average speed and the average velocity is just the direction. And you can calculate this by, let's say that you have a point over here and you have another point over here. Let me use another code. Okay. Rise over run, and then you find the slope. If you have the numbers clearly there, you're gonna be able to see that, or you can apply the equation, which is the difference in the position over the time interval. So you use the graph over here, the rise over the run, or you use this equation. You remember that the x is the position even though it's in the x-axis. Okay? Questions about that. Average velocity or average speed when you are using that formula. Okay. Questions? Okay, no question. We're gonna continue with this. So we have the average velocity and the average speed. Now the book is talking about the instantaneous velocity and speed. What is that? It's super simple. It's the speed or the velocity at any given point. Any given point. But I'm gonna give you a hint. Since we are going to be talking about objects that are moving at a constant rate, what's gonna happen with the instantaneous speed and velocity? Is the same at any given point because you have a constant rate of change. Miramos, it looks like we are in a math class. You are showing a graph, you're talking about a speed, you're talking about velocity, but you keep, using the slope formula, and we were learning that when we were in Algebra 1, okay? I know, physics, this is the class in which you're gonna apply all the things that you have learned in all your mathematics classes or your mathematics courses, okay? You're gonna apply all of that in here. And I was drawing this graph in there. It's a line. It's a line. Okay. So if this is a review for the what that are in your senior year, you're gonna be taking the SAT like pretty soon if you didn't take that over the summer. If I want to write the equation of the line, okay, in this case with that graph, the equation that I'm gonna use is the slope intercept point. Why? Because by looking at the graph, I'm gonna be able to find the y-intercept, and then see now I have information, I'm gonna be able to calculate the slope. Okay? So remember that if you want to write the same equation using function notation, position, because it's the dependent variable, in function of the time, which is the independent variable, is gonna be equal to the velocity, because you already know that the slope is the velocity, multiplied by time plus initial position. See that? And if you look in your book, you have that equation. Now, they were not using function notation. This is my function notation, in which this the same is the y-intercept, this is the slope, and this is my function notation. But if you want to write this in function of the dependent variable, so the final position is gonna be given by the velocity, which is the slope, times the time plus the initial position. And Ramos, what are you writing all of that in there? Because I'm gonna give you a graph like this. Okay, I have over here, okay, 40, okay, 40 seconds, que sé yo. Yeah, I'm making this up, okay? This subject, I think that is moving like super fast. I don't know, because I'm not analyzing the numbers. Let's say that I have a situation like this, and I want to find the equation that is describing that motion. Okay, perfect. See, the y-intercept is equal to 20. Okay, so I'm gonna write that over here. My final position is gonna be equal to initial position, which is 20 meters, velocity, that's my slope or speed. Okay, my slope, 20 meters in 20 seconds. 20 meters in 20 seconds, 1 meter per second. Okay, 1 meter per second multiplied by the time That's the equation that I can use. To find any given position of this object if the object continues moving at a constant rate. Let me rewrite this, because you know that in math, when you have a 1, you don't put that over there. So I'm going to put my meters per second times the time plus 20 meters. Ms. Ramo, do you have to put the unit of measurement? Of course, because okay, let's say that you want to find the position of this object after, I don't know, 100 seconds. What are you going to do? You are going to evaluate this using 100 in the time. So you will have meters per second multiplied by 100. You know that you have a 1 there. Seconds plus 20 meters. Second cancel con second. You have 100 meters plus 20 meters, 120 meters. That's why the equation of the line is useful. Okay? Because sometimes the graph doesn't extend to the point in time that you're looking the position. And by writing the equation, you can find that information. Questions? No? You don't have any question? Okay. This is our first problem that we have over here. First problem that we have over here. Okay? And before I start answering the questions, I want you to take a look at this. At the line that you have over here. The slope is a negative slope. Remember, what does that mean? That means that the object was moving, okay, see, if the positive part, you have that over here, if the positive part was representing the south, this object is moving, the origin is here, away from the point of reference in the opposite direction, so it's moving at whatever speed to the north. You see that I'm giving you that information there when I'm telling you that that part represents the south. Okay. Now, let me see what I have in here. So you have the graph in figure 21. That graph is describing the motion of a cruise ship drifting slowly through calm waters. The positive x directions along the vertical axis is defined to be south. Okay, they're giving you the information. X direction, remember that they are not talking about the x-axis. They are talking about the position, which is the dependent variable, which is the y-axis. Don't get confused, because if you get confused, remember, on the x-axis, always you're going to have the time. When you're talking about position, is the information that you have on the y-axis, even though they are using the x. Because that's a big misunderstanding that you have always on quizzes. Okay, is defined to be south. What is the ship's average speed? Okay, what do you have to find? You have to find the average slope. So slope. How you gonna find the slope? Simple. Variation in position over a variation in time. You can pick any point in there. Any point. Okay, so okay, let's say that I'm using, I don't know, let me use try always to find for whole numbers when you have a point with whole numbers. So I have that when the rise over here, see, okay, I'm going down, but you know that it's because it's moving at a constant rate. You know, it's that you're going down, you're going north. So you have 1 over 3, okay, 3 seconds. Meters, because you have the meter over there. So 1 over 3 meters per second, which is the same 0.33, repeating 3, meters per second. That's the average, okay. The average speed is 0.33 meters per second. I was rounding to the nearest 100 over there. Now, is that the velocity? No, because what is missing there? The position. The position of the duration. The average velocity. But as I was telling you before, in order for you to give me the duration, I have to give you information. The average velocity is 0.33 meters per second. Okay. North. And I'm going to extend, because you don't have that over there. You don't know if that is part of the other problems that you have over there. I'm going to extend this problem, because this is a practice problems that I'm doing for you, so you in the future you don't have any problem with this. Let's say that I want to find the equation that describes this line. Okay. Final position is gonna be equal to, Miss Ramos, now we have a problem because the slope of the line is negative. Do we have to put the negative over here? You don't have to. You don't have to, see? You don't have to put over here -1/3. No. But you need to know that when you are looking for the position, okay, so we're going to keep, because you can do these two ways. 1/3 meters per second multiplied by time plus 0, because starting the origin. So it's a, okay, let me see. This is a direct variation function. Point multiplied by time, because since it was starting in the origin, you don't have to put the 0 over there. Okay, this is up to you. That negative means that it's moving to the north. Okay, north is giving you the position. Let's say that you want to calculate the position of that cruise ship after, I don't know, after, let me see, 33 seconds. All right, 33 seconds. So when you come over here to your graph, to your equation, 1/3 meters per second multiplied by 33 seconds. The seconds, they cancel with the second. The final position is -11 meters. This negative is letting you know that it's going to north. If you don't have a negative, you have the wrong answer. No, you can't see. If you don't want to put that over there, that's fine. But you need to know that when you are looking for position, this is giving you the position as the object is moving all the way to north. Okay. Now in physics, the sign is helping you with the direction. Okay, and in this case, the sign is not affecting your final answer as long as you know where, see, the object is going. We're gonna continue, but I'm gonna solve problem 33 for you. Your job is to solve 34, 35, 36 with other problems that I'm gonna post on the classwork. Okay, so but we're going to do 36 together, and according to the duration that you have over here, you're going to use that figure that you have here. Now, Miss Ramos, what is happening here? A second ago we were talking about graph, and now all of a sudden I have over here a motion diagram. Okay, on Thursday, you were learning how to convert the motion diagram into a graph. So I'm going to do that over here. The origin is here. Origin is here. Okay, let me read the problem. See? Origin here, and between A and B, I have 25. So I know that my position is going to be expressed in kilometers. Okay, and I'm going to get information from my problem. Okay, the diagram at the right shows the path of a ship that sails at a constant velocity. Okay, velocity, constant velocity of 42 kilometers per hour is. See that? Is. So meaning that it's going to the east. What is the ship position when it reach point C? Over here. When it reach point 6. Relative to the starting point. If it sail from point B to point C in exact point B to point C in exactly 1.5 hours. Oh, mi Ramos, now we have a problem, because if we want to look at that information graphically, then we have to design a scale. Okay, we don't know over here how to start with the hours. You know what you're gonna do? You're gonna erase your graph, because this is the type of problem that you're not going to be able to solve graphically, because you need to find information, and then you have to find graph paper to make sure that you're plugging there the slope correctly. But they're giving you, okay, they are giving you the slope in kilometers per hour. Now you have to look for that scale and make sure that you have the correct scale, because otherwise you're not going to be able to have the answer. Okay, it's 1 hour and a half, it's a decimal, all that. So you have everything against you. Okay, against you, you want to use a graph. What do we have to do? We need to write the equation. See, diagram shows a ship at a constant velocity, constant. So I have equation of a line. Okay, and what is the ship? Okay, let me see. Let me erase that over here. What is the ship position? So we want to find the final position. Final position. Okay. If remember that the equation is a velocity plus initial position. What information we have over here? Okay, velocity, we know that. If we're gonna assume that is positive, even though you don't have that over there. What is the ship position? Okay, the diagram of a ship that sails at a constant speed. What is the ship position when it reaches point C? Point C, relative to the starting point A. That D that you have over here for the problem 33 is extra information. So you have to find the equation key, departing from here all the way through point C. If, okay, relative to the starting point A, as it sails, what is the ship position when it reaches point C relative to the starting point A? If it sails from B over here, B, all the way through the east, okay, is 1.5 hours. Okay. Initial position is gonna be equal to 0 kilometers, because it says over here A is the origin. Okay, so this term over here is 0. You have a constant velocity is 42. If we decide that is positive, 42 kilometers per hour. And then we have that multiplied by time. Yeah, I know what is coming to your mind. Okay, I know what is coming to your mind. Mi Ramos, the only thing that we have to do is just to plug the time in there. The time in there, and then we're gonna be able to find the final position. But you're wrong. Why? Because the problem is tricking you. See, it's very tricky. This is the origin, but you don't know this time over here. You know the time from B all the way to C is 1.5 hours. You don't have the time from A all the way to C. Now, you know that the distance between A and B is 25 kilometers. Where are you going to plug that in your equation? 25. If you represent that into a graph, this is the origin. And then you will be 25 kilometers over here, tracing your line at 42 kilometers per hour. Okay? So even though it's departing from here, which is the origin, you didn't have the information over there. The time that it took this chip to go from A all the way to B. And that's why you have to look at that as the y-intercept or the initial position, because after that initial position is that you know the time. Okay, so now you are ready to calculate the final position. See that? Okay, you have to be very careful when you're solving problems like this. Plus, okay, let me make this smaller because I'm not gonna have a space here. 25 kilometers. Let me use my calculator. Half of that, so it's 42. Half of that is 2. By 21 plus 42. 21 plus 42 is 63. Let me do that in a calculator, but I think it's 63. It's 42 multiplied by 1.5. 63. 63 hours. It cancels with hours. Plus 25 kilometers. When you add that, this is the final position. So it says over here, relative. What is the ship position when it reaches point C relative to point A, to point A? So the position of the ship is 88. Remember, is relative to, super important, relative to point A. And why this is important? Because if you want to find the final position relative to B, okay, the equation, see, the equation is per hour. This equation will have been enough. Relative to B, you solve with that. Relative to A, you have to add the distance between A and B because you didn't have the time that it took this ship going from A all the way to C. Questions? No? Problems like these, they look simple, they're not. This is physics. Okay.